All right, so we're pleased to have Omprokash Das from the Tata Institute, who's going to talk about the log minimal model program for Kahler threefolds.
Okay. First of all, I would like to thank the organizers for doing this thing. It's really a great thing going on. And it's a great pleasure to give a talk in this exact seminar. It has become something very important part of our daily life, I would say. Okay, so I'll talk about, I have been working with these things for a year now, okay, a little over a year, log minimal ordering program for Kahler threefold. So it's basically like we have MMP for projective varieties. So how far can you push those things? Can you do it on a compact Kahler manifold? Okay. So this is a joint work with two different papers. One is Christopher Haken, another one is Wayne Howell. Okay. So introduction. So the minimal model program for projective varieties of dimension 3 over complex numbers was fully established in the late 80s and early 90s due to the work of Miles Reed, Mori, Miyawaka, Matsuki, Kawamata, Kahler, Sokura, and many others. And also there was also a major breakthrough in high dimensions in 2006 due to Birker, Cassini, Haken, and McKernan. And those authors proved the existence of flips in all dimensions, and also the existence of minimal models for varieties of general type. All varieties are of course projective over complex numbers and in arbitrary dimension. So in the analytic category, one could ask a similar question. Is it possible to develop a minimal model program for compact Kahler manifolds? So with that, let's say we start with the compact Kahler manifold X. And if you want to develop a minimal model program for X by simply mimicking the methods from projective varieties, we would encounter an immediate problem. The first problem is the Morris bend and break technique. To produce rational curve, it simply does not work on Kahler manifolds because, well, that bend and break involves reduction to positive characteristic. Okay? So that is not available. So cone theorem would be a problem. Next thing is that another major obstacle is the base point free theorem. Okay? Base point free theorem for projective varieties basically gives us the contraction of kx negative extremal rise when x is projective. So the trouble here is that if a compact Kahler manifold contains a big line bundle, then immediately it becomes projective. Okay, that's a theorem of Namaki-Wak. I'll come back to this thing later again. Okay, so in particular, on a compact Kahler manifold which is not projective, the base point free theorem does not make sense. Okay, so that means even let's say somehow you got to the point of cone theorem, you have cone theorem somehow, you would not know how to contract the negative extremal rays. So without contraction, there is no MMP. Okay. So, but despite the failure of these two critical and technical tools, both of these two things are very crucial for MMP. Okay, but despite the failure of these two tools, there is actually no apparent reason to believe that why the MMP itself should not hold on compact Kahler manifolds. By which I mean that, well, those two things are basically gives a method, like a sufficient way of constructing minimal model program, but they are not necessary condition for the minimal model program. Okay, so there is no apparent reason to believe that why MMP itself would not hold on compact Kahler manifold. Okay, in fact, it does hold in dimension 3, as shown by Campana, Horing, and Peterndl. Okay, so before I actually go to the nitty-gritty of how do you actually do this cone theorem or contraction in Kahler manifold, let me just state the main theorem that Campana, Peterndl, and Horing they obtained. Okay, in dimension 3. Okay, so the first theorem is, so theorems looks almost identical to the, actually identical to the projective case. So let's say X is a Q factorial compact Kahler threefold with terminal singularities, and Kx is pseudoeffective. Okay, and then there is a finite sequence of Kx flips and divisible contractions, such that this x0 to xn, this thing, and the Kxn is nef. And similarly, if Kx is not pseudoeffective, then there exists a finite sequence of flips and divisible contraction. Then you go to Xn, and then there from Xn to Z, there is a vibration called modifier space, so that minus of Kxn is ample, and the relative Picard number is 1. This is a modifier space thing. So both of these two things is done in 2015 and 16. Okay. And then again in the same year actually, by Campana, Peterndl, Horing, these three, they also proved the abundance conjecture as well. Okay, that if you start the Q factorial, okay, actually you do not need Q factorial here, but okay, compact Kahler threefold with terminal singularity, and if Kx is nef, then it is in fact semi-ample. That means there exists a positive integer m, such that the line bundle, okay, take a subcell multiple so that it becomes actually Cartesian. Okay? The line bundle and also like a high multiple, this one will become generated by global sections. Okay? So these are the three main theorems. So what we did is, so yeah, there is another thing that title of this talk says log minimal model program, okay? But in this abundance paper of Campana, Horrigan, and Peter, they sort of did a partial version, a partial case of this log MMP, okay, for DLT pairs, a very special case where they assumed already that the KX itself is pseudo-effective and some technical assumption, which under some more technical, additional technical assumption, they needed to do this very specific, very limited log MMP. Okay, so the part of this thing was done there. Okay, so recently with Christopher, we did this, that the log version of each of these theorems. That let's say x comma delta be a DLT pair, where x is a q factorial compact Kahler threefold, kx plus delta is pseudo-effective, then there exists a finite sequence of kx plus delta flips and individual contractions such that we go to up to xn, and then the push for this thing becomes nef. And similarly, when it is not pseudo-effective, after finite many contraction, you have a modifier space. Okay, and also you have the log abundance. This work is with Wenhao O. This is not with Christopher. It's a separate paper. That let's say take a log canonical pair, x comma delta, and x is a normal compact Kahler threefold. If kx delta is nef, then it is semi-ample. Okay, so these are basically the results. Okay, that we did. Okay, so now I'll go to the preliminaries. Okay, so we'll start with an x be a normal analytic variety, and we'll work with the Bort-Chern cohomology of real closed 1-1 forms with local potentials, or equivalently a cohomology of real closed bi-degree 1-1 currents with local potentials. Okay, and this cohomology will be denoted by H11 BC of x. The good thing is that when x is a compact Kahler manifold, this H1 Bort-Chern cohomology is exactly same as the H11 x comma r, the usual one that we know. Now here's the thing. Since a compact Kahler manifold may contain very few divisors, or probably perhaps no divisor at all. Okay, so in those cases, the usual neuron-severity vector space NS, okay, that we have in projective variety, like a divisor quotient by numerical equivalence, is not suitable for MMP on compact Kahler manifold. It could be too small, this thing, or possibly empty, okay, or just finally many things. So we extend this thing. We define the n upper one as the Bort-Chern cohomology class, and then we know that this is from simple cohomology that neuron severity is inside of this n upper one. Okay, this Bort-Chern cohomology. Okay, and the interesting thing here is that the n1 of x could be strictly larger than the neuron severity even when x is projective. So even in a smooth projective variety, this could be larger. Okay, so you're actually considering a larger vector space than the neuron severity, even on a projective variety. One such example is this. So let's say x be a smooth projective K3 surface for the complex number. Then the H11 is a Hodge number that is always 20. It's a fixed number for a smooth projective K3 surfaces. But there are plenty of K3 surfaces whose Picard number, the dimension of the neuron severity, is strictly less than 20. There are lots of them. So this is actually considering a larger group, larger vector space. So this is so we have n upper one. So of course we would like to define n lower one then. Yeah, so in that case, so let's say x be a normal compact analytic variety in Fujigi class C. That means that x is bimeromorphic to a Kahler manifold. Okay, so this one is needed for some technical reason. Okay, the Fujigi class for this n lower one. Okay. Then n lower one of x is simply defines the dual R vector space of n upper one. And what are the elements of n lower one? I mean, of course, they are dual element, but they can be identified to the real close bidimension 1-1 currents, because n upper one is a form like if you think of n upper one as the cohomology classes of 1-1 form, then current of bidimension 1-1 are the dual of the forms. Okay. So that's what they do. And again, when x is a compact Kahler manifold, then n lower one is nothing but the n-1 x comma r, where n is the dimension of x. And within this n lower one x, we define this NAX. We'll call it a generalized modicon. This to be the closed cone generated by the classes of positive closed currents. Okay. Yeah, generated by the classes of positive closed currents, and the modicon inside this modicon lives inside this thing is defined as the closure of the cone generated by the currents of integration over a curve. Okay, so if you take a curve, irreducible curve, compact curve, you take the current of integration, that is automatically a bidimensional 1-1 current, positive and closed, all of it, this thing. Okay, so these things are there in any x. So NEX basically essentially cycle. Every one cycle will give you a current of integration, okay? Positive a current of integration, which is going to be effective. If it is effective one cycle, then it will be a positive current. Okay. So this is it. So again, it could be possible that even when x is projective, that NAX is strictly larger than the modicon, actual modicon. Okay. Even when x is projective. And the previous example I said is going to give you they give this counter example. Okay. The same counter example will work. Okay. Now the interesting fact is that, I mean, yeah, it's sort of that's how we define it. Okay, that n upper one cross n lower one, when you define it this way, take a class from n upper one, think of this eta as a class of 1-1 form, and this t as a class of bidimensional 1-1 current. Then this pairing, okay, that I'm yeah, the one bidimensional 1-1 current is a dual to 1-1 form, so I can evaluate it. So this is actually turns out to a perfect pairing when x has it has to have rational singularity for some technical reason again. Okay. So once we have this n upper one, n lower one, so next thing we're going to do is to define what is called a NEF class. Okay. So let's say again, x be a normal compact analytic variety in a Fuji class C, and U is a class in this Borchardt cohomology, or n upper one actually. This one is same as n upper one, represented by 1-1 form alpha. Okay, so one representative we are choosing it to be a form. Okay, alpha is local potential. Then U is called NEF if for some positive 1-1 form omega on x, and for every epsilon greater than 0, there exists a C infinity function. This f epsilon is a C infinity function, smooth function, such that alpha plus I del bar of f epsilon is greater than or equal to minus epsilon times omega. So you should think of this as this way, that this alpha plus this thing again stays in the cohomology class of U. So like you're just like moving this alpha by sort of like a rational equivalent sort of things when you compare with the projective variety. And then if this omega is, let's say, in fact, a Kahler class. Okay. Let's also think of this as like an amplifier. So like NEF plus, if you add this to the left hand side, bring this to the left hand side, a little bit of ample should be ample again, greater than or equal to 0. That's sort of the analogy. Okay. Now, if you take the NEF cone, the cone generated by all these NEF cohomology classes, that's a, yeah, let's take the cone generated by all these NEF cohomology classes called the NEF cone. And when x is dimension 3, it is proved in Horing Fraternal, one of the papers, first paper in fact in the series. The NEF cone is dual to the generalized modicon. Okay, so see, this is exact analog of the projective case where we know that the NEF cone is dual to the modicon. So that thing happens. There is a very unfortunate thing that you require the dimension of x to be 3. This is for technicality in the proof. Okay, that in higher dimension it would be that proof would not work simply. Okay. It would require some higher machinery, okay, that we do not know yet. Perhaps someone could try this thing. Okay, yeah. So far, okay, I have n upper one, n lower one, NEF cone. Okay, so let's define now what is a singular Kahler space, because if we want to work on an MMP, we know that even contraction for a smooth projective variety becomes singular. So similarly, that means if you start with a Kahler manifold, one contraction can immediately lead to a singular Kahler space. Okay, so what do you mean by singular Kahler space? An analytic variety X is called Kahler if there is a Kahler form omega, i.e. a positive closed real 1-1 form omega, such that the following holds. So you would essentially like to know, I mean, that what happens to the singular point of X, right? If you like take the smooth Lucas, there, well, sure, it is a manifold, possibly non-compact, but doesn't matter, it's a manifold, so Kahler manifold makes sense. So what happens to the singular point? How do you define that? So for every singular point X in X, there exists an open neighborhood U. This condition must be satisfied. Okay? So that when I embed U inside the open subset of Cn, there should exist a strictly pre-subharmonic C infinity function. Okay, such that when I do the I del bar of F and restrict it to the U intersection the smooth locus. Okay? That part should be same as the omega. So basically, I'm saying that even in a neighborhood of a singular point, like locally it should come as a pullback from something from an open subset of Cn, such that when I take the intersection of that open set with the smooth locus, that part, so that state should be same. That is it. So it's not too much required here. So in this definition, let's say X is a Kahler variety. And by the way, if X turns out to be actually smooth, in fact, even let's say X is a, the smooth analytic variety, and you define it this way, still this is going to be the usual Kahler manifold. Okay? So this thing is the actual real generalization, like good generalization of the Kahler definition. So if X is a Kahler variety, so let's say K inside of n upper one of X is a cone generated by the all classes of Kahler forms. Okay? Then from a theorem of De Mailly, it follows that nef cone of X is the closure of the Kahler cone. Okay, so it's like very nice. It's like you should compare, as you can see clearly that it compares to the projective case. The nef cone is the closure of the ample cone. So that already tells you that whenever you need an ample divisor, think of the Kahler forms as the ample replacement for ample divisors in a Kahler variety. Another interesting fact is that when X is a normal compact Kahler threefold with rational singularity, and let's say I just choose any class from the n upper one, and then this one will become Kahler if and only if this class intersects every class from the generalized modicon minus 0, this thing, strictly positively. So again, this one corresponds to the Clemens theorem in projective variety, that a divisor is ample if and only if its intersection with every non-zero class in the modicon is strictly greater than 0. So it compares to that. So it's like has very nice symmetry in that sense. Like there is a comparable thing that you can relate. Okay. So next we need two more definitions: pseudo-effective and big. Okay. So let X be a normal compact Kahler variety. A closed positive bi-degree 1-1 current T with local potential is called a Kahler current if T is bigger than or equal to omega for some form omega, some Kahler form omega on X. So you should really think of it this, that bi-degree 1-1 current means it should correspond to divisor, okay, well, a wild divisor on X. And then you are saying Kahler current, as I'll define in a moment. Next point is that Kahler current basically means it's a big divisor sort of thing. So, and omega compared to the ample. So you're saying a divisor is big if it is bigger than or equal to ample, because we know that big divisor is ample plus effective. Okay? So that thing means ample big minus ample is effective. So that's what it's saying. Big minus Kahler form is greater than or equal to 0 in the sense of current. So that's a Kahler current. And then a class is called big if it contains a Kahler current. Okay, so this basically sort of think of this as a numerical class of a big divisor. And then finally pseudo-effective. Okay? So a class is called pseudo-effective if it can be represented by positive current. Okay, so positive current means that locally it is of the form delta delta bar of some pluri-subharmonic function. So positive current corresponds to pseudo-effective divisor. Okay. I should not say correspond, but that's how we should think about it. Okay? The positive current should be related to the should correspond to the pseudo-effective divisors on projective varieties. And if you want effective divisor, you have to say not positive current, not only positive current, but it has to be current of integration. Okay? That is a positive current along the divisor if it is effective divisor, and then that is going to be a positive current, that is going to be effective divisor sort of thing. So current of integration along the divisor. Okay. So now cone theorem. Okay. So if you want to run a neural model program, the first thing that we need is a cone theorem. Okay, to decompose the modicon. Here we will decompose the generalized modicon. So when X is a compact Kahler threefold with terminal singularity, this was proved by Hording and Preternel, that the generalized modicon, this thing has exactly the same structure. Okay, So here's something very critical here. Okay, that when X is Q factorial compact Kahler threefold with terminal singularity, and Kx is pseudo-effective, this condition is extremely important. Okay, I'll explain later. Then there exists a countable family of rational curves satisfying this bound such that this decomposition holds. So it looks exactly like the regular modicon of curve. Okay? Here I see when Kx is not pseudo-effective. Okay, this cone there is a cone theorem, but it looks very different from the above description. Okay, so in the Kahler settings, you do not have a single cone theorem that works for both Kx pseudo-effective and non-pseudo-effective. You have to separate the unit and non-unit case, completely different like a parallel theory. Okay? There's a similarity that you can use one technique from another, but still there's a huge difference between these two. Okay? So they cannot be unified in one single cone theorem. In fact, what we do is that more specifically in that case, we actually need to make Kx pseudo-effective by adding some a Kahler class to it. Okay? and then decompose this cone, like this cone will be this, the right hand side will be kx plus omega greater than or equal to 0 plus negative extremal rays. Okay, so sort of when you have kx not pseudoeffective, we do not have cone theorem for kx, but kx plus omega for some scalar class. Okay, so I'm not going to say anything about that one at all because I just don't have time. I can only cover one of this thing. And this is the first thing that they do, and this is the most important one. The main idea, all the ideas come from the pseudoeffective. Okay, so this is one of the things that we do. That of course we have to when you want to do log MMP, that we extend their cone theorem to the log case. Okay, that when x comma delta is a DLT pair, x is a q factorial compact scalar threefold, and this is the kx plus delta is pseudoeffective. Then again, there is this rational curves with this bound, and then exactly this decomposition. Here, I would I'd like to point out that the proof of this thing is not a routine verification of the previous theorem of Harding and Prinell. Okay, you simply just cannot go back to their proof and then step by step just add delta and just have just a nice proof. It's not going to work like that. Okay, there are two main obstacles. One is that here, when I say kx plus delta pseudoeffective, of course, kx itself could be not pseudoeffective, right? Okay, so that is a problem. Okay, then the cone theorem before I said it looks very different. And secondly, that when they say terminal singularity on threefold, you have isolated singularity, and DLT singularity is non-isolated singularity. Both of these two puts a major difficulty in the cone theorem. Okay? So one thing that we have to do, like a very technical thing on the cone theorem for log case, is that before proving going to the cone theorem, we actually sort of have to prove the non-vanishing conjecture. Okay, that if kx plus delta is pseudoeffective, then there exists in fact effective q divisor d, so that kx plus delta is q linearly equivalent of d. Okay, and this sort of makes everything work better. Okay, that we can reduce a lot of the computation to the components of d. Go to surface. Okay, so the next major thing, once we do have a cone theorem. By the way, unfortunately, okay, I'm sorry. Let's go to this slide. Unfortunately, I'm not going to be able to say anything about that about the cone theorem at all. Like how do we overcome this bend and break taking and this thing. All of these things are a very interesting story, but there's just too many things that there too many things to tell. Okay, as a story of the whole thing. Okay, so I'm going to focus mainly this talk going to focus about how do you overcome base point free theorem. That is going to that is the main thing that I want to talk about today. Okay, not the bend and break part. I'm assuming the cone theorem there is. I'm not going to say anything more about that. Okay, so I'm going to focus on the base point free theorem. So once you have a cone theorem, the next order of business in MMP that is most important is that you need a contraction that lets you contract the negative extremal rays. Okay? In case of projective varieties, this is done using a base point free theorem. Okay, so let's recall our base point free theorem for projective varieties. So when x comma delta is a KLT pair, x is projective, and d is a Neff-Cartier divisor, so that k times d minus kx plus delta is Neff and big for some k natural number, then ox times md, this is given this line bundle is generated by global section. Okay, or in other words, d is semi-ample. Okay, so this is this. So as I said before, when x is a Kahler variety more generally with rational singularity, and if there is a big line bundle, then by theorem of Namikawa, x immediately become projective. That means on a compact Kahler manifold, you will never be able to satisfy the hypothesis that there is the difference is Neff and big. That simply does not make sense if it is not projective. Okay? Only Kahler but not projective. Yeah, so that's the thing. Okay, that on a non-projective Kahler manifold, this simply does not work. Okay? But firstly, there is a base point free conjecture on a Kahler variety, which is this. That in the analytic category, there is a base point free conjecture which mimics the statement of the base point free theorem in the projective case with the divisors now replaced by cohomology classes. Okay, so it looks exactly like this. That x comma delta is a KLT pair where x is a compact Kahler variety. And let's say alpha is a Neff class now instead of a divisor, now in F class. So that alpha minus kx plus delta is Neff and big in the sense of cohomology, of course. Okay. Then there exists a proper morphism with connected fibers f from x to z to a compact Kahler variety z. Z is Kahler with rational singularity such that alpha is a pullback of a Kahler class from z. And that is exactly what it means when you say that m times d is semi-ample. M times d is globally generated in the previous theorem. Okay. So this gives like a sort of an exact analog, but you have to replace divisor by cohomology class. So we saw that this theorem actually this conjecture does hold in dimension 3. Okay, that is our one of our theorem. Okay, So it's exactly the same statement, just the dimension of X is now 3, then this does hold. So here is the thing that this theorem that we did, this is actually not our completely original work, in the sense that this theorem is already proved in special cases, once by Tosati and Zhang, and other case by Horing. Okay, so the cases are this: that assume that delta equal to 0, X has terminal singularity, and alpha minus Kx is scalar class now, not just naive and big, but stronger scalar class. Okay, this is a non-trivial thing. Okay, that going from scalar to naive and big is a non-trivial thing. Okay, so assume this is a scalar class. Then this theorem was proved earlier by Tosati and Zhang. The case when alpha is only naive but not big. That means the contraction that you would get from Tosati and Zhang's theorem is going to be a contraction to a lower dimensional thing. For example, a modifiable space contraction type of thing. And the other case when alpha is both naive and big, then you would get a bimorphic contraction that was done by Horing. And this naive and big part, this the second one that was done by Horing is actually harder than the other case, the previous one, in some sense. Okay. Unfortunately, I mean, you would think that, okay, now that we have this contraction theorem for a log version of contraction theorem, we would simply use that to contract Kx plus delta negative extremal rays, but that is not the case. Unfortunately, this theorem, this contraction theorem that we have, log version, in our paper, okay, is proved as an application of log MMP. Okay, so in particular, it cannot be used to prove the contraction of Kx plus delta negative extremal rays in the generalized molecular form. In fact, the proof and Horing's proof there and the special case, that is also using the MMP they have, okay, that for terminal singularity and delta equality. Okay, so yeah, so there is, in this case, however, the F alpha naive but not big does not involve MMP. I think, I don't remember it, yeah, using MMP there. Okay, but this case they do, and so do we. Okay, so that means this theorem is sort of just only an application of the log MMP that you already have. Okay, so that means still we do not know how to contract negative extremal rays. Okay? So here comes this classical theorem, blowing down theorem in analytic geometry. Okay? It was originally, I think, by Grauert, and then there was some generalization by Fuzigi, and then later on a further generalization which is more applicable is by Ancona and Tan in 1984. Okay? So it says this, that let X be a complex space and Z be a closed complex subspace of X. And suppose that there exists a proper surjective morphism G from Z to W, okay, such that the conormal sheaf of Z inside of X is ample when restricted to the fibers of G. In other words, the conormal sheaf is relatively ample with respect to the morphism G. And also assume that the natural map, this thing, is surjective for all n greater than or equal to 1. Okay, then the conclusion is that there exists a complex space Y that contains W as a closed complex subspace and a proper morphism from F to Y, such that like outside of X, Z and W, it is an isomorphism. In other words, F is a bimeromorphic, and then when I restrict F to the Z, it immediately becomes G. Okay? So it's sort of like going other way around, right? Okay, like you already, so think of this thing like if you take, let's say that let's take a Y to be our a threefold, okay, and take a curve inside of it, a smooth threefold Y and a smooth curve. W is a smooth curve. You blow up the smooth curve. Let's say the accessional device is E. That E is your Z here. So sort of you already know that you have accessional thing that you want to contract to certain thing. Okay, like you have to know where you want to contract your thing. You have to know the target. You have to know a morphism for that. Okay, and then you say that you extend your domain and and like a target space around X, Z, and W, so that you get a bimorphism. Okay? So like very strange in some sense. Okay, that yeah, like it's completely like in some sense like unintuitive. Okay, that how do you do this kind of things. But it's true, and this is what actually Horing and Pitton they use originally, okay, in their proof for terminal singularity and delta equal to 0, and this also for some part we use this one as well, okay, and other part we have to do something else. Okay. So okay, let's see how much time do I have. Okay, I have exactly almost 20 minutes. Okay, 21 minutes. So I'm going to yeah. So before I go any further, okay, see that before I actually show you how to contract using this theorem, how to contract negative extremal rays. Other thing that I'm leaving out here is that you might be wondering that in MMP, this contracts in a projective case, the contraction theorem, Weismann-Freer theorem, these are not the major obstacle. The major obstacle is the existence of Fleef and termination of Fleef. So what about those? Okay, so let me just tell you one slide about that, and that will be it. We are in luck in this case. The flipping, if we have a flipping contraction, then the existence of Fleef in in three-dimensional Kahler variety is completely free. Because of this, that when X has terminal singularity, the existence of the flip A plus directly follows from Mori's proof, since his proof is analytic. Okay, so it's free. Similarly, when you have a log canonical pair and is kx plus delta flip, so flipping contraction F is, then it's, flip X plus is again due to Sokurov, and again his proof is analytic proof. So again, we get it for free. And also the termination of flip is also analytic proof. It's a local proof through discrepancy and other invariant, also analytic in nature. Okay, so that one works too. So the major hurdle in projective MMP, that is the existence of flip, which is of course we know now because of BCHM over complex number. But in general, I'm saying philosophically that is the hardest thing. That is actually kind of free here. Okay? The existence of termination of flip. Okay? Fortunately, I mean, thank God. Okay? Because there are already enough problem in the Kahler category. So the main difficulty for us is going to be not the proving the flip, but how do you do the flipping contraction or the divisorial contraction. And surprisingly, you will see the flipping contraction is not the hardest thing. The divisorial contraction is the hardest thing in the Kahler category, which is kind of very weird. Okay. Okay, so I'm going to talk about this this proof of Harding and Peternel. Okay, that how do they contract kx negative extremal rays? So you have terminal singularities with empty boundary. Let me show you the steps, because this actually gives the best picture. Okay, the log version that you did, it becomes quite technical. Okay, so let me do their thing. So let's start with X compact Kahler threefold with terminal singularities, and let's say again I'm assuming Kx pseudoeffective. I'm not doing the other case at all, the modified cases, only the pseudoeffective case. Kx pseudoeffective, and let R be a Kx negative external ray of this generalized modicon. Then just as in the projective case, you can show that there exists a Neff class alpha, so that alpha par intersect with generalized modicon, which is basically all the classes from generalized modicon, so that alpha dot, this is 0, this is exactly R. So we simply say that R is supported by the Neff class alpha in this case. And then maybe you have to rescale alpha, but rescaling alpha, you can show that using the Kohn theorem, this generalized modicon theorem, that alpha minus kx is a Kahler class. So write it as omega, so alpha equal to kx plus omega. Omega is a Kahler class. Then note that alpha equal to alpha is actually a big class. The similar kind of thing that actually that works in projective variety works here, that kx is pseudoeffective and omega is scalar. So pseudoeffective plus scalar is actually big. Compared with the pseudoeffective divisor plus ample divisor is a big divisor, sort of things. And then if it is big, then it's a theorem of Buxom that that is going to be big and Neff, so it's omega cube must be positive. I think this thing actually, this direction is actually easy. Okay, it's positive. So yeah. So what you do is next is that consider the null locus of this alpha. So union of all positive dimensional subvarieties such that alpha to the power dimension of v dot v equal to 0. First of all, you immediately notice that this null locus is not the entire X, because we know from the previous slide that alpha cube is strictly positive. Okay? So it's a subset of X, but in general it could be a countable union of proper subvarieties of X. Okay, so but it's actually a very famous theorem of Collins and Tosati that this null locus is in fact a closed analytic subset of X. Okay, that works in actually arbitrary dimension though, although you would need a manifold in higher dimension, I guess. Okay. With some work that it can also be shown that the null locus of alpha is exactly the locus covered by the curves in the extremal ray R. Okay, so like you need to do some work, it requires some work, okay, technical work, but you can show that thing. The null locus is exactly like if I take all the curves in the extremal ray and take the locus in X, that is exactly the null locus of X. So now there are three cases. Okay, the null locus of X, alpha is a finite union of curves, or it's an irreducible surface, so that the alpha restricted to that surface is numerically 0, numerically trivial, or it's irreducible surface but alpha restricted to S is not 0. Okay? These are going to be three cases. So see, I mean, if it's a surface, then I know that alpha squared dot S is going to be 0. That does not necessarily mean that alpha restricted to S is 0. Okay, so this is why the two possibilities. Okay? So let me show you what you do in these cases. Okay, so let's start with the first one when there's a finitely many curves. Okay, so let's assume that Z equal to the null locus of alpha is a finite union of curves. So remember, we need to use the blowing down theorem. We want to contract this Z. Okay, so that means I need to say that I need to know that there has to be a morphism from Z to some target space. Okay, which satisfies a bunch of properties. Okay. So what is that morphism going to be? Okay, so we propose that since I know that I want clipping contraction, that those curves should go to points. I mean, curve only can go to point, of course. Okay, so we choose the morphism G to be simply the map that sends a connected component of Z, connected component of Z to different points. Okay? That's what maps G. Now the difficult part here is the showing that the conormal sheaf of the Z is actually going to be this G ample. Okay, when restricted to the fibers of G, it's ample. Okay, that part is actually the difficult part. So in order to do that, this is what you do. Okay, we actually go to a higher resolution of X in order to do that. Okay, so this is how it goes. That by theorem of Buxom and Colin-Tosati, there exists a projective bimanifold morphism from a scalar manifold, basically resolution of singularity, X prime to X, such that the null locus of alpha, remember alpha is in X. Okay, so null locus of alpha becomes the image of the exceptional locus of this mu. In other words, by simply blowing up the null locus, you can go to like a sort of a Kahler manifold. Okay, and then pullback of and also the pullback of alpha, it was an F and B class, becomes now a Kahler class omega prime on the Kahler manifold, dimension 3, plus exceptional divisor. And this exceptional divisor is going to be an effective exceptional divisor. Also, the support of this is going to be the entire exceptional locus. Okay. Here's the next thing. Let's take a curve in the null locus of alpha, right? Okay. So here, and then yeah, so the curve here, what I see that since alpha is, so alpha dot C equal to 0, that means alpha restricted to C is numerically trivial. Then do this, that restrict both sides of this equation. Oh, sorry, no, I should say this, that remember that since everything is a threefold, X prime and X, image of this E, image of the exceptional divisors are either a point or curves. That's what it is. Okay, so it's going to be curve in this case because I know for a fact that the exceptional image of the exceptional locus is the null locus of alpha, which is consists only finitely many curves. Okay, so when I take a curve from the null locus and I take the inverse image of that curve, okay, by mu and restrict it to both sides, that becomes the one of the component of the E, right? And then there it is going to this side is 0, so the right hand side is also 0. So similarly, we will simply get that minus E to the power E. Sorry, minus E restricted to E is numerically equivalent to omega restricted to E. Just restrict this both sides to the E, okay, and then I know that E is this way. E has this property, and then alpha restricted to C is numerically trivial. That will imply this. So see, the left hand side is a divisor, and right hand side is a Kahler class restricted to a divisor. Okay, so since omega is a Kahler class, omega has this property that it will intersect every positive dimensional subvariety positively. Okay, or in other words, that minus E restricted to E, this is actually a globally an ample divisor on E because right hand side is scalar. Okay, so a line bundle, if is given a line bundle numerically equivalent to a Kahler class or Kahler form, is automatically an ample line bundle. It's positive. Okay, therefore it is ample. So that's what happens here. Okay, so E minus E restricted to E, that is exactly a conormal sheaf of E. Okay, so this is this is globally an ample divisor on E. Okay. So when it's a globally ample divisor on E, so you can think of this thing. So forget about this this thing. Okay, let's think of it here. Okay, so this is a globally line bundle on E, ample divisor, this conormal sheaf. So remember that thing that E goes to the curves on E is on X prime. E goes to curves on X, and those curves goes to point by this G. Okay, so you're thinking all the way from the E to the points. Okay, so since this is already globally ample, that means this thing with respect to that G from all the way X prime to the points does satisfy that the conormal sheaf is a ample divisor. So a conormal sheaf is relatively ample. Okay, so then therefore I can apply the blowing down theorem. That there is a morphism from X prime to Y which contracts the connected components of E to points. Okay, so I have now X prime to Y. I needed X to Y. So then by simply rigidity lemma, we can factorize this X prime to Y via this through X to Y. Okay, and then that automatically implies that the null locus of alpha will actually contract to finitely many points. This is our tipping contraction. Okay. So next is, let's see, 10 more minutes, right? Okay.
Yes.
So, okay, thank you. So next is that null locus of S, alpha is, let's say, S, okay, and alpha to the restricted S is numerically trivial, okay. In that case, you can simply show that S restricted to C is strictly less than 0 for all the curves which are contained in the extremal ray R, okay. And then this is a simple trick using Kohn theorem that alpha minus some very small multiple of S will become strictly positive in the generalized modicon minus 0, okay. So in particular, by the criteria that I told you before, this is an Kahler class. So that means alpha equal to omega, epsilon S plus epsilon. Now restrict both sides to S, since alpha restricted to S is numerically trivial. This minus S restricted to S is again an ample divisor on S, and this is of course again the conormal sieve of S, okay. So I simply say that, okay, let's say that I choose our G, the morphism G, to be S to a point. I want to contract the surface to a point. So that's what we are doing. So then this is a global ample divisor. So again, by blowing down theorem, you will have that you can get this blow down theorem that if S will contract to a point in this case. Okay? So the last case is that null of alpha is S and alpha restricted to S is not numerically trivial. Okay, this is the hardest case here. Okay, and I mean surprisingly hard this is. Okay, so see in this case you can say that since alpha restricted to S is not trivial, you could say that I mean it is true that two arbitrary point of S cannot be, okay, sorry, so typo, cannot be connected by a chain of curves which are all alpha trivial. Okay, it's simply not possible. That's like a if and only if criteria when a class is nef or a divisor is, sorry, when a class is numerically trivial, okay, or a divisor numerically trivial. In particular, it only tells you that the nef dimension of alpha restricted to S should be 1. But in order to use the nef reduction map, you need to have a normal variety. You cannot do it on a normal variety. Okay, so we need to go to a normalization S tilde to S. These are all Horing pattern proof. Okay, this is not ours. Okay, they're original proof, these things. So we go to normalization and pull back this alpha restricted to, this should be alpha restricted to S and then pull back by the normalization. Okay, then take the net reduction map. Okay, net reduction will have dimension 1 because of course square of this thing is 0. We know that. Okay. So this is net reduction 1. So when net reduction 1, then the net reduction map is actually a morphism. Okay, that's a very nice thing here. Then the whole thing is that we want to show that this G tilde descends to a morphism from S to B. That is the difficult part here. Okay, that's a very difficult part. This turns out to be a surprisingly hard problem. Okay, so what is done is that when X has terminal singularity, then a computation of intersection number shows that a very delicate computation, a very carefully chosen thing. Okay? A computation of intersection number shows that S is smooth in a neighborhood of the gel fibers of this thing. Okay? That's what happens. And then explicit computation shows that G can be descend to a morphism this. And once it descends to that morphism, and the rest of the things falls apart, you can show that again that the relative, the conormal sieve is relatively ample because conormal sieve is minus S restricted to S, and then I know that all this curve that the fibers of these things are exactly the elements of the curves in the extremal rays with which S already has negative intersection. So minus S restricted to S dot C is simply minus S dot C, which is positive. Okay, so that's relatively ample. So then again you can use the blow down theorem. That is done. So okay, very nice. I have 6 minutes. Okay, perfect. So we do exact same thing for log pairs because this is how we contract our extremal rays. Okay, so we have now a DLT pair, and then assume that we have a R is a kx delta negative extremal ray. So again, by the Kohn theorem that we already have, we can write alpha equal to kx plus omega plus delta plus omega, and the same property that is supporting class. So again, we consider the null locus of alpha. If the null locus of alpha is a finite union of curves or irreducible surface, and that alpha is to that surface is numerically trivial, then the proofs are again simpler. Okay, although the flipping contraction, the first case, the finite union of curves, that case is now harder because it's harder and technical because the singularities of X is now non-isolated singularity, but still not that hard. Okay, and both of these two things is proved in the compound parallel Horing abundance paper. Okay? What we do is that we do the other case, that when alpha is S but alpha restricted is not numerically trivial, this case is very hard. Okay, and since X has S does not have an isolated singularity, it's just that thing that they did by descending is simply does not work. You cannot do that thing. Okay? However, when S has semi-log canonical singularity, this is already done in compound parallel Horing. Okay, but sort of arranging that S has semi-log canonical singularity is kind of a nearly impossible task to achieve They can do it because their only focus is doing abundance, where you have a bunch of reduction theorem, where you basically show that the thing that you are contracting comes from your boundary divisor, okay? And your boundary divisor is canonical with key factorial singularity. Therefore, one of the component will have semi-log canonical singularity, okay? So that's how they manage it. But for us, that is not the case. It's a general thing, okay? So this is one of our main theorem actually, okay? So apart from, I mean, this is one of the main theorem that that lets us do the log MMP, okay? That this is actually how we started this project, joint project, okay? And that I wanted to do this thing and do this kind of thing. We wanted to, okay? So there's a DLT pair, threefold, okay? And then Kx plus B is pseudo-effective, and R is a negative external rate supported by NF and B class, okay? So that this is an irreducible surface, okay? And yeah, then there exists a positive morphism. Like we are doing all the cases at the same time here for divisorial contraction, okay? That you can contract, so the extensional divisor exactly, yes. Let me just give you very quick. I have 4 minutes, okay? So again, we do there also alpha. Again, we can do this thing, do this business that I can write alpha equal to Kx plus B plus some Kahler form. And then we immediately reduce it to a problem of KLT pair, okay? That replace B by, again, there is a mistake here. B by 1 minus epsilon times B and omega by omega plus epsilon times B, okay? This is not correct. Then it becomes a KLT pair. And then we do this, okay? We choose a birational model, okay? So that mu is that is an isomorphism over the outside, over the complement of S. So like basically outside of S is an isomorphism. And then we have X prime comma delta prime a DLT singularity where delta prime is given by this. Strict terms of B plus 1 minus B times S plus the extension locus of mu, where B is the multiplicity of S inside of B, if S is contained there at all, okay? Okay, and then basically we write this equation, okay, where S prime is the strict transform. We can write it this way. It's numerically trivial over this pullback of alpha, okay? And then basically we run Kx plus delta prime MMP, so that every step of this MMP is this alpha prime trivial, okay? The good thing is that this MMP can be run, okay? That like you would say, well, before even having MMP, how do you run this MMP? Well, this MMP can be run. Again, the only problem is the divisorial contraction, where your, you know, the null locus of alpha, sorry, now alpha restricted to the S is not numerically trivial, that part, right? But now that part is very nice. See, all of these things, this is a DLT pair, right? So every step is DLT, okay? So let's say at the ith step, I call the boundary divisor to be delta I prime, okay? So yeah, so and look at the right hand side. The round down of delta prime is actually completely contained in the right hand side here, okay? So whatever I'm contracting in this MMP, I'm contracting everything from the right hand side. So if I contract a divisor, I'm contracting one of these things, which is containing the round down of delta prime. When delta prime is DLT singularity, then every irreducible component of the round down of delta prime has normal singularity. Okay, so they are DLT, they are normal. Every DLT centers are normal. Okay, so that means the divisor that will contract Fi, that is actually already a normal divisor. Well, when it is a normal divisor, simply take the alpha that gives you the supporting class of the extremal ray, restrict to this Fi, and just take the NF reduction, because now this Fi is already normal, okay? And then that's it. That immediately gives you the NF reduction is your that G, and then you can do the blowing down theory immediately right there. Okay. So for this special MMP, we do have divisor contraction, so you can run MMP, and the next step we saw that that after we run this MMP, at the end of this MMP, the right hand side becomes completely zero. In other words, it contracts this S prime, the strict transform of this S as well. Okay, that thing that we wanted to contract, this S. Okay. And then final step is so that when I go from X to X prime, this birational map is in fact a morphism. Thank you. Okay, I finished 1 minute early.
So thank you very much for this very nice talk. So any questions by chance? So I have a question actually. I'm just waiting if there are others. There was a remark in the chat that read is spelled R-E-I-D instead of R-I-E-D. Okay. So.
Oh, sorry.
So besides that, I have one question. So if you take a case-free surface, which you mentioned, the typical examples where the H11 doesn't agree with the neuron severity. So then this type, the scalar modicon, is bigger than the usual modicon, right?
Correct. Yes. Yes.
So you have contractions. You have non-projective contractions somehow that.
Correct. You could do that. Yes, you could do non-projective contractions.
That you cannot see on from the traditional modicon.
Actually, see. Okay, now I have to actually. I'm not sure because see on the negative side, the modicon and the usual modicon and the generalized modicon, they actually kind of look same on the negative side. Okay, so the way that the Kohn theorem is proved, that you first saw that if the modicon has this decomposition, then the generalized modicon has exactly same decomposition. Okay, so the negative part, they're actually kind of same.
Oh, okay. So are all these contractions that one constructs in this scalar MMP, they are not all projective, right?
No, they are not all projective. No.
They are not all projective.
Because what will happen is that once you do the contraction, birational contraction of a Kahler manifold or Kahler variety is not Kahler in general. This is Fuji class C. Okay, then you have to show that there is a Kahler form. Okay, the way that you show is that using this thing that
I'm
the
sorry,
class is
I
Kahler.
lost connection.
Oh, can you hear me now?
Just the last sentence or so.
Okay. Yeah. So sorry. What I was saying is that once you do a contraction in the negative external ray of the generalized modicon, that becomes only a Fuji class variety. Okay. So you will need to find a Kahler class on that. So the way you do that is to sort of push forward something Kahler from upstairs, and you forcefully show that intersects the generalized modicon strictly positively. Okay. That's a criteria that's showing that is actually a Kahler class. Okay. Sort of.
Okay, I see.
It's not automatic. The images of a Kahler is Kahler. Okay. Which in the projective case, if you do it through the base point free theorem, it is always free and for free. That is a projective, right? Here, these things are not free in this case.
So I see. So there are extremal contractions which are not projective in general, but somehow not for case-free surfaces, or that's the message.
So what I would think that I have to think about this thing, that if in the negative part, if the modicon and the Kahler and the generalized modicon, if those are exactly same thing on the negative part, then yes, even though it's a like a contraction of a negative externally of NA, it would still end up being projective. I mean, initially you will have it Kahler, but of course projective is Kahler, right? Okay.
And this thing that is the same in the negative part, the two cones, this is particular to case-free surfaces or something general?
No. It should be. So the thing is, okay, I actually haven't seen a direct proof, but the way the Kohn theorems are proved, it looks like that. I mean, they also say this thing that they look similar on the right-hand side. Okay.
So this is more like a conjecture. That's actually the
not conjecture, like a, yeah. I mean, I'm just thinking. Okay, see. When you say negative external ray, it's already represented by a curve, even for the generalized modicon. Okay, so if all of those are curves, so that means that is part of the modicon, original modicon as well, right? Okay. So yes, I would say that they are actually same on the negative side. I mean,
so you don't get actually new contractions. I see. So okay, so if you start with the projective variety, you don't get new contractions.
Yeah, but again, like so. Okay. You have to see how you're doing a contraction. Like, I mean, it will be the result is projective, but you have to prove it then forcefully. Okay, like if you do not use base point free theorem, these techniques do not give you, they automatically give you to a projective. Okay. That's the point.
Okay, I guess we should finish questions around here because we have 5 minutes strictly for questions. So thank you again for the lecture.
Thank you.
So I stop recording for this one. Thank you.
Okay.